All right, so welcome to the CS109 final review session. My name is Will. Thank you. Okay. I'm one of the TAs. I'll be leading this section. So first up, here's CS109, the general advice. Usually students focus on how to apply formulas from class, maybe try to get a numerical answer. And these are like, okay, so one example, how to take a derivative from an MLE. Okay, that's actually that's quite challenging. But also once you know how to take a derivative, it's pretty straightforward to take a derivative. The hard part is usually the modeling. So log likelihood, actually finding the distribution for a log likelihood if we don't tell you. So on that note, especially for the final, for those of you that have seen the practice finals, there is a lot of reading. Every single problem has 2-3 paragraphs of just straight context, and then 3 bullet point questions that come right after it. So in the same sense, the midterm exam had 6 questions or 5 questions or so, with very small amount of reading and a lot of problem solving. On the final, similar number of problems, a lot more reading, and expect a few more parts. Okay? So please read the problems very thoroughly, and then the problems should be doable. Okay? All right. So here's how to read probability in the final exam edition. So to make this slide, I kind of went through the first final that I saw and just took a look at, okay, what's the most common paradigm that we saw? What's the most common amount of words? By the way, these slides will be posted later. So first things are what's the probability of blank? This is in 3 out of or at least one of the subparts on most of the problems that I've seen. How much more likely? And then okay, so in that case, you want to write a probability of something. A very common one we also see is how much more likely is a blank than a blank. Usually this means you want to be dividing 2 likelihoods or PDFs or products of PDFs. In in the discrete case, this would be 2 probabilities, and you'll be dividing them. Okay, so we also see the word yes.
What do you mean by likelihoods?
Oh, likelihoods the product of a PDF. So P7 for problem 7. There was a, okay, maybe I should explain what that is. It's just this thing. Boy, your likelihood is like this. You just, at some point in time in one of your pieces, you have something that looked like this, right? Or I guess it wasn't theta at this point. It was A, X given B. It was A and X given B, right? I have to duck my head down to use the microphone. So that's what I mean by likelihood. This is technically this is kind of like a form of a likelihood. Okay? All right. If we say the word parameterize and don't specify the method, which we probably will specify the method, it usually means you're going to do one of MLE or MAP, and if you're going to be doing MLE or MAP, find the data. Find what your sums or what your products are over. Especially I think on the last section we had a problem about setting up a boba place on campus. There was a hidden data point in there somewhere that you had to do MLE for. It was a single data point. So that could happen. Okay? If we say approximate, so during the midterm, approximate just means use a Gaussian or a Poisson approximation. And on the final, all that means is if you see a set of random variables, go on ahead and just use CLT. Okay? That's usually what approximation means here. By the way, caveat, if you use CLT, make sure the continuity correct. Continuity correct is everywhere. I did not put them in the slides because that's kind of a thing we covered before the midterm, but remember to do that here too. Is blank significant? Usually that means a bootstrap or a p-value. So typically write an algo or show hey, count some things and be hey, the p-value is greater than 5%. Probably not good, so. Okay. All right, so with that, we start our journey with betas. Betas are the first things that we saw that were clearly post-midterm material. And in a beta, the way the beta distribution is set up with 2 parameters A and B, and they represent A-1 heads and B-1 tails from a biased coin Y. So betas are always typically characterize our belief over a Bernoulli, and they represent the probability of a Bernoulli parameter given certain amount of heads and a certain amount of tails. Okay, the betas are in the range 0 and 1. they have a form of a PDF with some parameter, with some like constant b that is like, that we write explicitly later. The important parts are the expectation and the variance. So these are like two values that I saw come up in like one of the practice exams. I have an example on this like the end of the slide, so we'll take a look at it more. But generally, the reason why we put beta distribution after the midterm and in its own thing is because the beta distribution actually like it captures something about the parameters of a Bernoulli. Like before, we just had like Bernoullis or like just like binomials about like random events. Now we're like, okay, what's the probability of like of a particular theta in like a Bernoulli? Okay. All right. Then we talked about adding independent variables. So the three most heavily used forms that I've seen of adding random variables are like adding Poissons, adding normals, adding binomials. They all have to be like IID. Like so like if they're independent of each other and they're from the same Poisson distribution and you sum them, you can like that's like just like summing to the lambdas. Okay. One particular example of this is like in EVGR A, there's 3 elevators. If both of the other elevators are out of service, the amount of people that are going to be trying to go into an elevator or they're going to be trying to go into the last remaining elevator will be 3 times lambda, assuming each one of the elevators is like has a Poisson of lambda for students trying to use it. Okay. The normal distribution. So okay, when you add normal distributions, you want to be adding variances. You don't want to be adding standard deviations. So that's why we put the sigma squares over here. So straight like if you have two like normals, you add the mean, add the variance, and then like one particular example of this is like okay, like heights are typically normally distributed. So if you have like people like sitting piggyback on top of each other, that's like the sum of 2 Gaussians on the height. Yeah, it just literally taller. And the final one is on binomials. So binomials is like if you have like whenever I think of binomial, I think of like trials and I think of like some underlying like Bernoulli event. Like I have a coin, I'm trying to flip it, I'm trying to get however many heads or however many tails. So one example to think about like binomials is you and a co-author are conducting the same experiment, right? And then but you ran N1 trials and your co-author ran N2 trials like independently of each other. Like what is the probability distribution of like your results from like if you like coalesce the two sets of trials together? And the solution is well like just add so you just increase the number of trials. You didn't change anything about the underlying parameter. So you're just going to have a binomial of like number of trials for one plus number of trials for the second one. Okay. So this is adding independent random variables. Yes.
Previous slide, there's a constant in front of the beta distribution.
Yeah.
B.
Yeah.
What does that mean?
That's not a course reader. It's some complicated number. Yeah. Like we have it in the slides, but like I just yeah. It's a constant. Like you can normalize it out usually. Yes.
We need to know that constant for the final.
We'll probably give it to you if you need it, honestly. But real answer, you got 10 pages of review sheets. Just stick it on like the margin of one of them. Okay, all right. Any other ones? No? Okay. So here's a central limit theorem. There's kind of two flavors of the central limit theorem. You could take the sum of x IID random variables, or you could take the average of some IID random variables. One example of some IID random variables is given enough trials, anything looks like a normal. So if like those like that little graph of like if I just keep rolling dice, the sum that I'm going to get from those dice is going to eventually look like a normal, and that's like the approximation that we're going to use. Average of IID random variables, these actually are used a lot in denoising. So like if you the one example is like sample means are normally distributed. So like the bigger your sample mean, the less variance of those kinds of means that you will see. So like the better, so that's like a tighter average that you would find. Okay, makes sense. So this is like one of the critical theorems that we use, and we actually give it a name. Okay, all right. So the next thing that we have is sampling. So in sampling, we actually saw how to find the sample mean, the sample standard deviation. And typically, whenever we sample, the image I have in my head, or the one that we have from the class, is like here's some underlying distribution. you construct some like sample histogram, and then each one of these points becomes an equivalent class of that kind of point. So that will be important later on in bootstrapping, but just know that you're like trying to construct something that looks similar to what your underlying distribution f looks like. Okay. So sample mean and sample variance are two particular quantities that we can talk about. They are unbiased, meaning that the expected value of all of the sample means that we could possibly take is actually going to be the mean. And the expectation of like all the sample variances should actually come out to be the sample, should actually converge to the variance. Okay? All right, makes sense, looks good. Okay, so then we took an interlude and started talking about algorithmic analysis. I put bootstrapping after this, I promise. So there was some want about how to do, about like another example of algorithmic analysis, stepping through it step by step. Okay, and so I conjured up another example of recurse. So I took the recurse from lecture, and then I like made it a little bit more complicated by adding in this like random variable q and some like, and the for loop that like actually increments based on whatever q is. This should look like problem 9 from pset 6, no, from pset 5. Yeah. So this is the one where like, okay, like we actually need to show that like q is independent of something. All right, so here's a law of total expectation, and the prompt that we're given is, okay, what is the expected return value of this recurse function? Okay, so how do we start this usually? All right, our target is expectation of x. So random variable, call the function signature the expectation. Then we replace the recursive function signature with the expectation of x everywhere we see it, and it matches like verbatim. Okay, so here we'll return we replace the recurse on the return statement with 7 plus expectation of x. Okay. Now where it gets complicated is, in the for loop here, we technically have expectation of x times q, where q is this other like uniform distribution here from q. Okay? So the way we work with that is, well, we see that whatever our choice q is here is going to be independent of whatever this recurse is going to return us. So we can just make the independent assumption here and say that expectation of x times q is equal to the expectation of x times the expectation of q. Okay? So after that, okay, return 3. 3 is 3. So no expectation here. It's just this. All right. Yes? Oh, sure. So in the for loop here, the value that we're going to be returning here is like, okay, depending on whatever q is, like the random variable here is like big Q, and then the random variable that we're going to get out of recurse at every step is some x, right? So when you have two random variables and we're looking for like how many, like they're independent of each other, and you're trying to multiply them. So like first you'll say, okay, the two random events multiply each other, and then you say, okay, they're actually independent of each other. So you can just split up the expectation here by independence assumption. There is one thing that's kind of tricky here is that like, one question is like, okay, is Q, like if we were to think about this outer E of x, is Q independent of this outer E of x? Or sorry, let me put it the other way. Is the outer E of x here independent of Q? The answer is no. But the trick here is that the inner recurse has like another random variable x. This is not actually the original x that we had at the outer scope of the function. It's the one from the inner scope of the function, meaning that this should be like xi or something, drawn from the same distribution as this x over here. Okay? So that was one thing that kind of came up a few times on an ed post, but should be reasonable. Okay, does that make sense to everyone? All right. So plug in 3. Okay, now we just put it all together and do some math. So we multiply each one of the branches by their expected value. So we use the law of total expectation. The probability of entering this first branch with 7 plus recurse is 1 out of these 10, so that's 1/10. The probability of entering like the recurse here is another 1 out of 10, so that's this term right here. Then 8/10 of the time we return 3. The reason why I chose 1/10, 1/10, and 8/10 is because if I made it any bigger, the expectation is actually infinite, and when it's infinite, we can't really apply the law of total expectation, but that's a detail. Okay, so now we just start summing. So summit, we distribute. Like you got 10 expectation on the left, 6 expectation on the right, and 31. Collect the terms and solve, and you get 31 over 4. Did that make sense? Should I like go through that a little slower, or we good? Okay. Yes.
Should it be 37 over 9? Or no, never mind. I
9?
didn't see the multiplication. Sorry, my bad.
Okay, cool. I mean, I would not be surprised if there was a typo in this. This was written late at night.
I didn't see the multiplications.
Okay, all right. So now there's bootstrapping. So when we visited bootstrapping, it was from sampling. We cared about 2 values when we were doing sampling, and it was the sample mean and the sample variance. That means that our 2 flavors of bootstrapping are going to be over means and over variances. So what that means is the typical bootstrapping, actually, I have a good example of this. I can like just know the structure for bootstrapping of means and bootstrapping of variances. The key difference is you'll be like calculating a mean on the resample, and then you have a distribution of your means. On the variance version, you have a variance of your resample, and then you have the distribution of your variances. These are the 2 most common forms of like bootstrapping that we're going to throw at you in this class. And I'll run. So here's an example of like how to do the Corgi problem that you guys saw in section. So I realized that the Corgi solution that we had on the website actually has really like jumbled up like a lot like overleaf. So I took the step solution we just made an example out of it. So here's what we're going to state is there's 2 islands worth of corgis. We want to say that island B's corgis have a 3-inch higher variance than the height of those in A. Okay, so if we look at the heights of the corgis in islands A and B, we want to assert the claim that island B's variance is higher by 3. Okay? The way we do that is, okay, here's the population of all the corgis. We draw population 1 from the island of corgis in island A, and we draw a population, oh, that's supposed to be 2. Great, there's a typo. Population 2 is supposed to be from corgis of B. Okay? And then we like combine them into like a general population and start resampling. So the way we start there is, okay, so this blue part is the execution of the code. So we first create the total population of all the corgis. Then we enter a for loop and we say, okay, so we repeat the following 50 times. Notice that we only repeat resampling from the total population and not resampling from like the space of all corgis or from like islands. Like a good way to know this is like your researchers have already left the island, so they can't really go back to take more corgis, right? We could only have so many corgis. So okay, so repeat 50 times. And then the first thing we do is we resample 2 samples from the total population. And then once we resample the 2 samples from the total population is, okay, this part's going to be fast. We're going to do like 5 lines of code in one. We take the count. So we look at the difference between the sample variance of island 2 minus island 1, and we look at the difference. If this difference is greater than 3, we just increment by 1. So that's exactly what the sign is saying. And 1 here is the indicator random variable that says, okay, if this like random event so happens to be true, we'll increment 1 into the count. Okay, does that help? Like, any questions? Yes.
So this is an example of a bootstrapping problem where we'll be calculating p-value. Will we maybe see an example of one of the other ones, like that we saw before, in like calculating mean variance, where rather than combining 2 populations, that we just have like 1 subpopulation? So, like in the mean happiness example from
right.
class, like all we did was just have like a subsection of the population. Like we didn't like take 2 and then recombine them.
Oh yeah, I didn't put that in the examples because that was a lecture example already. So I was thinking like I was trying to give something that was like not too far from the lecture, but still wasn't like totally like redundant.
So like could we potentially see both of those types of problems?
But also, like, if we give you guys a bootstrapping problem, right, we're not going to go give you like a giant list and say, okay, take a sum over all of these. That's not like at most we'll say, hey, here's like 2 or 3 samples. Yes, in the back.
Why are you taking the absolute value of that difference when you want to show that island B, so like sample 2, has a higher variance?
Oh, it's because we want to see, okay, like we want to see if we take the the corgis from island A and island B and put them into like a total population, we don't actually know like which one of these corgis came from island A and island B. And what our p-value is trying to show is, hey, even if I don't know, like there shouldn't like the claim about the variance shouldn't just appear in nature. Like it shouldn't just appear if I just like randomly like combine these two samples and then just started taking like resamples. So like the idea is like if like population A has like if we combine population A and population B and we just suddenly start seeing, oh yeah, there's like differences in like the variance is like greater than 3, just like in general, then the claim is probably not good. So that would actually give us like a higher p-value. So like the higher the p-value is, higher in the probability that a hypothesis is null. Does that kind of explain it, or?
Okay, I think I was just a little confused because like sample 2 would be a different size, and then variance is also dependent on like the size of the sample. But so you should always take the absolute value of the difference.
It's getting like tail test and one tail test.
Yeah, one tail test and two tail tests. Yeah.
This is a two tail test, right?
Yeah. Okay. You have a two. Okay. As per what is yours? If you have a two tail test, take the absolute value. Okay.
Two-tailed, what is it?
Do we need to talk about? Okay.
We can talk about this offline, I guess.
Yeah, maybe clarify it offline. But in general, like if you have a total population here, right, and you like try to split into two samples, and you take the difference, right? Like you don't know if you're proving that they're smaller than by 3 or bigger than 3. So like keep the like. Short answer is yes, but be cautious about it. Don't. Okay. The problem will probably tell you if you should take the absolute value or not. Okay. All right.
Where did we get the 3 from?
Oh, 3 inches higher.
Oh.
3 inches higher. Yeah. It was in a prompt. Yes.
Is there a time you would ever sample without replacement during bootstrap?
That's called a permutation test, and no. Yes. Okay. All right. Next. All right. Parameter estimation. Okay. So this is a very old meme, according to my associates. So in parameter estimation, you have the problem will probably ask you, what do we want? And you'll say, we want the parameters, and what do they look like? Some Greek symbols, or P, or A and B. And these are given to you like, okay, if you have a Bernoulli, your theta is going to be a P. If you have a Poisson lambda, your theta is going to be a lambda. If you have uniform A and B, your thetas are going to be A and B. If you have normal, so you're going to be mu and sigma squared, right? So questions like, okay, why is theta the only one that's like left isolated here? It's because we will conventionally, like the first Greek letter we think of whenever we think of parameters is theta, probably because it's easier to write or so. So yeah, so this is parameter estimation. Okay. All right. Then here's maximum likelihood estimators. So whenever I think of MLE, I think of like a two-step process. Like the first step is to find the likelihood. The second step is to optimize it. So likelihood here is a big product over all the PDFs. Usually you want the log likelihood because we want to take a derivative of it. And then once we find the derivative, we can actually solve for the argmax of the theta. So to solve for argmax of the theta here, you would either use gradient ascent, or you would set the derivative equal to 0 and solve. We will most likely tip you off about which one you should be using on a problem, so you don't like spend too much time trying to solve for 0 on like or trying to solve derivative equals 0 on a problem where you should be using gradient descent. And typically those forms are like describe an algorithm. Oh, maybe I should have put this in the English part. Like if a problem says describe an algorithm to optimize, you almost always want to go to gradient descent. If the problem doesn't say that, there is a chance that you could solve it using the idea that the derivative should be equal to 0. Okay? Make sense? All right. So here's MAP. What's the difference between MAP and MLE? Right? So what I wrote here was I put the 2 steps of the MAP on the left, and I put the 2 steps of the MAP on the right. So MLE is on the left, MAP is on the right. Oh, I should have labeled these a little bit better. So in MLE, I'll update these slides to actually say that like there should be like an MLE here. In the left side over here, you just have the PDF. On the right side in the MAP, you have some prior g of theta here. We will almost always give you what this theta is, and the only point is it's multiplied. So the okay, I put a big space here, but these are actually multiplied by each other. And you wanna find the optimal parameter, like the argmax of this likelihood where they actually multiply by each other. Okay. The main difference is here in your argmax function, you will have a log of the g of theta added to your original like argmax target for MLE. Okay. So I mean, like just for exposition, go back one. Like you're just taking the argmax over like this product, or over the sum. And here you're taking the argmax over like that sum and the log. Okay? That's the main difference. Yes?
So the right is the MAP?
Yes, the right side is the MAP. Yeah, I should. Yeah, I had labels on these, but then I think they got shifted around when I was trying to like squeeze in the map. Yes?
The key difference is that an MAP includes a prior.
Yes. So the MAP is like if you had a friend that has already done some experimentation on this and you want to use their work. Okay? Yes.
Then, by virtue of that, MAP would be slightly more accurate than MLE.
If your friend is a good friend and gave you correct data, that's not noisy. Which is, I mean, good friends could accidentally give you like bad data too. Yeah.
Is that why MLE is just more common then?
MLE is like, you need MLE to solve MAP. So we like introduce MLE first and then MAP.
Oh.
Why it's more common? It probably is more common, but I'm not quite sure. I don't actually know the general claim of that. Yes?
Will the problem tell us like whether we need to use MAP or MLE, or will that be given like?
If it gives you a prior, that's a tip off, right? If it gives you a prior, you should probably use the prior. Yeah. Okay. Alrighty. So next one is here are MAP priors. I put this slide on here just for exposition, but we will almost always give you these. But the idea is like whatever your like MLE estimate is, this will actually influence what your prior should be. So if your like estimate is like a Bernoulli, you want to almost always use a beta to be your prior. And these are like the whole conjugate distribution things. So like you guys don't have to know like every little detail about conjugate distributions because we will almost always give you whatever prior this is here. And all you guys need to know is how to use it in the MAP sense. Okay? I mean, cheat sheet wise, you have 10 pages if you want. Like just write down the names of these distributions and their parameters and maybe like a one sentence about like what they do. Or like, I don't know, while on like a bike ride or something and you're waiting for like a parking spot, just like whip out a phone and like check it. What else? Okay. All right, so that's about MAP priors. So here's the general machine learning paradigm. The idea is someone gives you data and they want the optimal parameter because it's totally a fair trade. Oh, yes, sorry. Sure. Before you start trading? Okay. Yeah.
What is the
The Dirichlet is the conjugate prior of the multinomial. So, you know what? Look at the course reader. They'll probably tell you. Look at the course reader. We have a description of it. If you have to use the Dirichlet, we'll give you the parameters for it. Okay.
sounds good.
Yeah. Let's go trace some parameters for datas. All right. So in machine learning, typically what you have is some real world problem. You want to model, and then you want to model the problem and using a formal model theta. Here is typically where you would find like log likelihood. And then you will have some training data. So this is the indices on your sum. And then you have some learning algorithm. And this learning algorithm is usually like how you optimize the theta. Okay? And then since we're all veterans on p set 6 by now, here is the testing data. And you're supposed to just get a score after you get out this optimal parameter. So just a brief high level about how the machine learning things work. We might ask you like a true/false question about some parts of the data pipeline, but we're not going to give you like a 30-pointer on just hey design a machine learning model for this. Like that's a little hard. Okay. All right. So after that, we saw naive Bayes. Naive Bayes is just using the independence assumption, where like if I condition on a y, then all the xi's are independent. It's naive because we're trying to condition on the independence. So what's the hard parts about the naive Bayes is we're given these like tuples of like xi and y, and we're trying to actually predict like, okay, what's the optimal y here given these labels, right? And the thing that you typically want to do is a Laplace smoothing, which means, okay, add 1 to all your numerators, and then add 2 or however many to your denominators, so the data set is still balanced. And usually this is just like a counting problem, where like, okay, you just count the number of times where xi equals xi, and big Y equals little y, and you divide it by like the samples where like y is equal to little y. Okay? And then when you do a prediction, no need to do a derivative here, no need to do like any gradient ascent, nothing of that sort. Just loop over all your y's, look at your data, do a few sums, spit it out. That's naive Bayes. Okay? Yes?
Can you explain what p hat means?
P hat? Oh, P hat is actually probably is the probability that we're like our estimated probability that y is the actual y. Yes, that we're gonna try to like derive here. So P hat is like our estimate of like whatever the xi equal of like the xi and y. Okay, so this is the thing that we actually find in training. Yeah. Yes, it's the approximate. Whenever you see a hat, it's approximate.
Okay.
Yes. Yes,
Is the probability of y hat being 1 same with 1 minus the probability of it is 0, the direct Laplace prior?
Sorry, y hat might.
Right. You plug in 0 for y.
Sure.
Right.
Uh-huh.
It's 1 minus that.
Yeah.
Probability that y hat is 1.
Probably that y hat is what? Conjugate? That's if y is a Bernoulli. That's if y is a Bernoulli. If it's 0, 1. Y can be 4, cos 4, right? Like it could be like happy face, smiley face, sad face, and angry face, right? It could be like size 4, right?
Yeah.
Yeah. Like if y is a Bernoulli, yeah, you can do 1 minus. But if it's not, then
So in this case, 0 or 1.
yeah, in this case, yeah, because it's 0 or 1. Yeah, like it explicitly says like 0 or 1. Okay. All right. So next, here's logistic regression. Logistic regression, in my opinion, is like MLE with a Bernoulli. But the thing about a Bernoulli is it's a discrete random variable, so we had to like go conjure up a PDF for the Bernoulli. Okay, that's where we get the inspiration for the log likelihood. Yes.
Could you explain how MLE and MAP fit into like naive Bayes and logistic regression like one more time?
So I can explain how MLE fits into the logistic regression, because it's just logistic regression where your PDF or your likelihood function is chosen with the PDF of a Bernoulli distribution. Mm-hmm. For MAP, like MAP is like what happens if you have like a prior, but in naive, like, okay, so MAP to logistic regression, you can have a logistic regression problem that is like solvable using like MAP. So like if I give you a prior about this Bernoulli, right, and it's going to take the form of a beta, then you can solve. Then you just have another like data point for your like prediction algorithm. How naive Bayes fits in is a little bit more tricky, because naive Bayes you're taking the independence assumption and you're just counting, like I don't know. I think yeah. So.
It's like little parameter estimation.
Just p hat. Like your parameter estimation is honestly done online. So like it's kind of like you have to loop over your whole data set every single time you want to do a prediction, which is like that's like the key difference between like MLE and like naive Bayes, right? Okay. All right. Good. All right. So with that, I have a bunch of problems lined up, or 2 or 3 or something. I think it's like 2 or 3. Yeah. And I'll walk through them slowly. They're not going to be like that bootstrapping example where there was like 4 lines worth of like problems. But, sorry, no, 4 lines worth of code done in one comment. That won't happen. But, so here's the problems. So the first one is an MLE example. It's about how to do reliability engineering. And here's a problem where they say, okay, we have a random variable characterized by A with some PDF, this, and we wish to know how long a particular model of a phone will function before it breaks. That's what this PDF is here. We are going to use a reliability distribution. To this end, we collect n independent measurements of how long the type of phone functions before it breaks x1 through xn, explaining words how you would choose parameter A using the MLE framework and provide any necessary derivatives. Okay, so what are the key data points here? What's our parameter? A. Where's our data set? x1 through xn. Which algorithm are we using? MLE. What's our likelihood? This thing right here. This like big equation. So how do we map this to our two-step? We draw arrows and say, okay, the f, just replace this strictly with our f. Take the data points x1 through xn and replace xi with them. Theta hat here and normal theta here, replace that with parameter a, and then we apply the MLE training. We apply the estimator from the MLE. Okay. So to that end, I wrote out all the steps. We're going to move the problem up the upper right, and I hope that's not too small. People in the back, are we good? Ish. Okay. So first, we need to find a log likelihood. So we're given the likelihood first. So we take the log. Yeah, we just apply the log and put an L on the left. Then we swap the log and the product, so it becomes a sum over the log. Is it too small? Is that? Okay, that's x squared j and this is x squared j and a squared. And then we use some more we use the log rules and start splitting up the terms. So this is just like if you have like multiplication in your log, they're like added. Use log rules again to bring your exponents down. Okay, now you have like this fully like almost simplified like summation term. And then just break up the sums a little bit so it's easier to do the derivatives. Okay? Okay, and then like take out a few terms. Like there's no, this term right here does not rely on I at all. So you can just sum over all n of them, and that's negative 2n. Okay? Any questions about how we went from likelihood to log likelihood? Assuming the text is not too small for people in the back to see. I realize that this might be a bit small, but the slides have all the numbers. Yes. I mean, sufficiently simplified to take a derivative. Yeah, I mean, this is sufficiently simplified. We're also not gonna be like, hey, how much did you simplify your log likelihood? It just has to be simple enough that you can actually take a derivative in like a reasonable way. Okay. All right. So now we take the derivative. So step 2, optimize. So to optimize, we need to optimize with respect to our parameter a. So that's just, okay, take the derivative of this giant thing down here. And then if we apply the derivative to each one of these terms, we said, okay, this becomes like negative 2 over a. This becomes like just log of xi. This becomes nothing because it's just, there's no a term here. And this is like positive 1 over a cubed or so. Something of that sort. And if you propagate the derivative and simplify, you get just those terms that we saw. Yes. So these are not the same terms because we dropped the a from this term about it here. Okay. So then I think at this point, yeah, you set the derivative equal to 0 and you can solve for a. So one way that you can know that you can solve for a here is that there's only one parameter. Like we saw in a section problem where there was like 2 parameters. I get both like mu and sigma. But here you only have a. You should be able to solve for it. If you don't, that's probably okay. Yes.
Have 2 parameters you're trying to optimize.
Mm-hmm.
Just take the partial with log likelihood with respect to both parameters. And then
Yes.
optimize that.
Yes, and then in that case you would have like 2 partial derivatives, right? You would have like, well, you know what? Here we only had like partial LL over partial A, right? In that case, oh man, that does not look like A. In that particular case, you would have like partial LL over partial mu and partial LL. So you have like this thing and then like comma partial LL over partial sigma. And then so you'll take the derivative of both of those and then try to optimize. Usually if you have 2 parameters that you need to optimize for, we don't expect you guys to solve, setting it equal to 0, and you will just use gradient ascent. Yes?
Now, can you optimize both the mu and the sigma independently?
One will become, so if you can solve for one parameter in terms of the other one, then yes. But if you can't, like if sigma is dependent on mu and then mu is also dependent on sigma, then it's not so simple, and you need to use ascent. Yes. Yes. Sorry.
Why is the sum terms in the middle?
Oh, the sum terms in the middle? Are you talking about this term? So this one, we're taking the derivative with respect to a. So take your partial derivative, pass it into, oh, here, I have a laser pointer. So we take this partial derivative with respect to a, pass it into the sum, and then you know that like sum and like the partial derivative, I can just pass the partial derivative into the sum. Then just take, okay, partial derivative of a times log of xi is just log of xi, which is this exact term we have down here. Okay? And then this, like, this sum term just disappears because there's no a in there. Cool. Yes?
So for the first, on the last on the solution, we got negative 2a over a because of negative log of a, right?
Yes.
Okay.
So log a here, just the derivative here just becomes 1 over a times negative 2n. Yeah. Cool, cool. Yes, keep asking. The derivatives are hard. We should practice them. Okay, all right. So, yes. Oh, sorry, yes.
So for optimization, MLE and MAP, will we mostly stick with taking the partial and setting it equal to 0, whereas gradient descent will mostly stay in the realm of logistic regression?
You could actually tell if the problem wants to use gradient descent or not sometimes. We'll say at the end, give us like a 3-sentence algorithm about like how to, okay, this is also not a promise because we haven't decided yet, but like you should, like, usually at the end of a problem, if it tells you, hey, give us like a 3-sentence thing about how you would optimize it, that typically means you can't solve it by setting it equal to 0. But if we don't say anything, you might be able to solve it equal to 0, and might as in, even if you make a mistake along the way somewhere, you can always just fall back on gradient descent, and we'll give some partial credit for that.
And we can just explain gradient descent in words.
Oh, I have a slide with gradient descent, right? Like, oh, it's too far back. But in the slides, there is a gradient descent, and you can just be like theta new equals theta old minus partial derivative LL theta, done, right? Yeah, you could just write that and be like, oh yeah, just execute this in a loop or something. Yeah. Okay, all right. So here's an example about how to use betas and how to do pseudocode. So let's say that we have observed some 30 successes and 20 failures for an event with unknown probability. Based on this information, we can model the probability of success x as a beta random variable. We want to make the claim of the form, the probability of success is m plus or minus b. Okay? So we need to select m here to be the expectation of x, select b to be the smallest value rounded to 2 decimal places, such that probability of m minus b is less than like x less than like m plus b is greater than or equal to like 95%, and provide your answer as a pseudocode that prints out the values m and b. Okay? So here are some key points that I had on the first pass of this problem, but looking at it again this morning when I didn't have time to edit the slides, there's another 2. So, here, the bolded part that I just forgot, didn't box in, rounded to 2 decimal places. Okay, what this typically means is somewhere in your pseudocode, you'll be doing a grid search. Okay, what does that mean? That means that if I'm after some value, like, oh, they're both used, okay. So if I'm after some value, say x, right? I want like x between like a and b. There should probably be like a for loop in there that does like x plus equals like 0.01 because they say up to 2 decimal places. And you're just going to be looping through this until like break if you have some condition on x. Okay? So this is like a grid search kind of strategy where you're like, okay, like you just want to like sweep over all the possible values of x up to some precision, and it will return to the value that you need. Okay? All right, so for this particular problem, we have a starter function. Yes, because everything starts with main. And then we need to combine the 30 successes and 20 failures into a beta. So here, the beta that we need to initialize is a beta with 30 plus 1 and 20 plus 1. Plus 1 because we always want to initialize beta with an extra 1. Okay, as per like normal like beta initialization. Then we say, okay, they want something of the form m. So we know that the m here is the expectation of x. So we use the second point here for like finding what the expectation of like what the beta is. Okay. Then now, okay, So how do we find x? Like we're given that it has to be accurate of like 2 decimal places, and it has to be within this particular range, and it has to be greater than like 0.95, right? So the way we do that is in a for loop. Okay, so here's what I'm supposed to say. Just increment it slowly. And the way we do it is here's a while true. So in the while true, so here's the loop that actually does a grid search approach. We want to say that okay, x has to be greater than like the lower bound, which is just the mean minus x, but it has to be like less than like the upper bound, which is mean plus x. And then the probability of that region is the CDF of whatever the upper side is minus the CDF of whatever the lower side is. And if that's greater than 95%, which is our target, then we break it. Otherwise, we continue on with our grid search. Okay? And then just print it out. And then just like print out the values. Does this make sense? Like, hope I didn't go too fast. I see confused faces. I see crowds. Yes?
It's that x with the plus equals 0. Is that like for the x?
Oh, this is so we're trying to find x, right? And the way that we find it is by doing grid search. Oh, I guess, yeah. Oh, sorry. It's not, okay. This is a bad naming convention. We call it x, but it's actually b. So we're looking for like the smallest value b here. That could like that, and that's why we have like b's here, like the minus x as b's over here. Yeah. Okay. I'll go edit the solutions and actually change it to b, because otherwise it's a little bit misleading. Yeah. Yeah, because like we can't really train on that. Yes.
So how do you like know that it's a grid search approach, and like would there be like another way to solve it if you like didn't get to that? Or?
There most likely is another way to do it, but I didn't peruse through the solutions for this particular problem. But the thing that tips it off that it's a grid search is here. Like we want b rounded to 2 decimal places. So typically, if you want something rounded to something places in a code and it's like approximate, it usually means like, okay, like I want to like increment it slowly somehow. And that's typically like grid search. Like, okay, I have a boundary on the left, I have a boundary on the right, I'm gonna just increment it until it's done. And sometimes we'll like even provide a range. Like here, we didn't actually provide a range. Like we just said, okay, while true, just find a region of B that will like actually just satisfy this. And we're gonna pretend that we're guaranteed that this will terminate. Like in all respect, like in real life, like this whole like while true loop might actually never break, because it's possible that the probability is never like, well, actually no, it will break, because eventually x will become so big that it becomes 1. Yeah. Okay. Sorry. Yes, we're actually moving the range this way.
Oh,
yeah, we're expanding the range.
Oh,
yeah. So at some point, like, the thing is we're after like the smallest value of b, right? And then at some point we're going to get b so big it's going to be 1. But then we don't want that b, we want the smallest one, such as like greater than 0.95. Yep. Okay, yeah, we want like tightness of like lower bound. Okay. So I think that was the last question, that was the last example that I had. Okay, and yeah, so I saved like the last like 15 or 20 minutes for just like general questions about like the final exam or for like parts of 109. We can also revisit the slides if people have questions about that, but other than that, like, yeah, that's all the material I had. Yes?
Yeah, so on one of the practice finals, it had like a question about like deep learning networks and like some math about that. But then on the like final like on the website it says like you're not going to be expected to do like deep neural networks. So
yeah, like
is there just not going to be any deep neural networks only up to like logistic regression? Or?
Even if we give it to you, we'll make it reasonable. So we're not going to be expecting you to take like vector gradients or anything like that. We'll make it so that it's doable with the stuff that we covered. So in a problem like that particular final, what likely happened was, so in past iterations of 109, we used to have like derivatives where we could people have like, it's actually possible to be like, okay, find the gradient of like some like the the log likelihood, right? Or do like what's the partial log likelihood with like respect to like some like array of like A's, right? And that's probably going to be something like, I don't know, like X transpose something, right? We never did that in class. Don't worry about it. We will not give you this in the exam. Even if you have a neural network with multiple nodes, it will probably be like solvable just using partial derivatives on like each one of the elements of like whatever like small network we give. Okay. So yeah, all right. Any other questions? If not, we can we can have 20 or so minutes back and good luck on the final.
Woo!